Okay, and then we're going to do it here. Here. Good. So everybody will talk about Blackbox design space.
Okay, thank you. Yeah, first want to thank the organizers for what's been a really, really fun and exciting conference so far, and I'm sure will continue to be. And to thank them for allowing me to speak today. I'm going to talk about some work with Andy, Alfredo, and Noah from last year. Two of whom were in the audience, one of whom will hear from tomorrow, on black holes in time space. So, to start off with some motivation for time space, we've already heard some from a few of the talks so far, but working Q2 or the Kleinian signature has really emerged as a super useful tool in both celestial holography and the Amplitudes program and other places like twisters even. And this is for several reasons, more than I can list on the slide. The first being scattering amplitudes really simplified. We can use on-shell methods and have some really nice, precise tools to simplify our expressions pretty dramatically. On-shell massless 3-point amplitudes can be generically non-zero in Kleinian signature. This doesn't happen in Lorentzian, and with Euclidean signature, you can't have the on-shell condition. So this is a really nice feature of Klein space that we can use these super simple 3-point amplitudes that can give us a lot of information about larger and amplitude structures. We can have quantum self-dual gravity in Klein signature, and this is a really useful toy model for more complicated theories of quantum gravity. And as Shruti mentioned in her talk on Monday, we can have this self-duality condition on the Riemann tensor in 2-2 signature, not in the Lorentzian signature. And finally, as we heard, many useful celestial holography results have come out of working in 2-2. See the celestial sphere, here comes the celestial torus, nice Toric Penrose diagrams with simplifications for our bases for scattering in 2-2, and many other things like taking holomorphic self limits, any place where we're taking Z and V bar being real and independent, we're implicitly working in. So an outline of both the paper and the talk today is really combining a lot of these motivating factors. So the first part I'll talk about is an analysis of some global Kleinian spacetimes, so 2-2 signature spacetimes. You can find Penrose diagrams for them. Do they have any interesting properties? We'll find out they do. And in the second part, we will pivot to looking at linearized spacetimes. So leading order, Newton's constant G. And actually find a way to really utilize this really useful, simple 3-point amplitude to allow us to reproduce a classical metric from the classical limit of the 3-point amplitude. And finally, I'll very, very briefly, if there's time, making sure you all get out to lunch reasonably quickly, talk about some future directions that we're working on in taking this bulk construction to the celestial torus. Great, so starting off part 1, global spacetimes. The most interesting example for us was the Taub-NUT spacetime, which is a generalization of Schwarzschild, where we have the usual mass m as well as a nut charge n. This is kind of, you can think of it as a magnetic mass, and kind of dual to the usual mass in a similar way to electric and magnetic charge being dual.
Sorry, I had a
yes.
super, yeah, tell me. You said this was the one that was most interesting. Why?
I'll get to it. Essentially, we can find after we analytically continue to Q2, when we take n equal n, this is a self-dual spacetime, and that turned out to have some nice properties, both for writing about the Penrose diagram and in relation to Kerr-Taub-NUT.
This is the ability to find it. Okay.
Yeah, I'll get it if you're still wondering. So here's the expression for the metric. It's not, you don't need to memorize it or anything. We take n to 0, get short shield. Now we want to take this to Q2. So we'll whip rotate some coordinates. There's a lot of different choices we can make. This is one in particular we chose, both because, as you'll see in a second, it gives us a nice Penrose diagram. And it also has a nice connection to our Amplitude story in the second part of this talk. But yeah, by no means is this the only analytic continuation we can choose. Two things to note: we'll rotate t and theta. When we rotate t, it becomes periodic in the same way that when we go from Lorentzian to Schwarzschild, the t coordinate becomes periodic. And similarly, we'll rotate theta, and that will become non-compact now. It will lose its periodicity. And we'll rotate n in order to keep our metric. Yeah, so as I mentioned, if we set n equals to n, this metric is self-dual, in the sense that the Riemann tensor is self-dual. And here's the expression for the metric. So for the remainder of the talk, I'll be looking at this self-dual n equals n, at least for this problem. Great. So Andy mentioned in his talk on Mondays briefly some aspects of these toric Penrose diagrams. I'll briefly go over in case you missed. If we start with flat plane space, so take two space-like coordinates, two time-like coordinates, we can rewrite those in terms of polar coordinates for each. So R is a non-compact coordinate, psi is a compact coordinate identified with 2, 5, and similarly for rho and 5. In the usual way, we can compactify along the two non-compact directions, one being space-like, one being time-like. And we end up with this Penrose diagram. It has, as Andy mentioned, one component of null infinity, and it's a toric Penrose diagram, and then each point in this diagram is a Lorentzian torus, so one space-like compact direction and time-like compact direction. And yeah, this was a line in this paper. So we wanted to go a similar route to find a toric Penrose diagram for this self-dual Taub-NUT. And we can essentially do a very similar thing in this, in our metric here, sorry, for the W's of coordinates. T and phi are our two compact coordinates, and R and theta are our two non-compact coordinates, one time-like, one space-like. So we can compactify along non-compact directions, yielding a Penrose diagram. And there's nicer coordinates we can choose that isn't one overall with a bunch of coordinates. Some salient features: there is one component of null infinity, same as the flat case, as well as a horizon where the coordinate choice breaks down, but we can move through with like coordinates, as well as a singularity at r equals minus m, in the sense that the Frenchman singularity, so Riemann with Riemann has a singularity there.
The new wire singularities.
Not in this, but wire singularities come from it's kind of what if you want to have generic m and n, you can, yeah, it's like it comes from that. Otherwise, you can have like n equals 5 orders and something like that for how old m is. Yeah. Yeah, and as similarly to other case, toric Penrose diagram, each point in the diagram, we're suppressing the Lorentzian torus. Great. So moving on to some more spacetimes, we can think about what happens when we add an angular momentum parameter A. So if we take Kerr-Taub-NUT, this is Taub-NUT adding in A generalization of Kerr with nut charge. I won't write out the metric for you, but we can perform a very similar with rotation, rotating the same coordinates t and theta, rotating n and a to keep our metric real. We obtain Kerr-Taub-NUT, and the interesting piece we found here is that in the self-dual case, so when m equals n, Kerr-Taub-NUT is also self-dual. And there's actually a diffeomorphism between the R and theta coordinates used for Taub-NUT and the R and theta coordinates used for Kerr-Taub-NUT, which maps Kleinian Taub-NUT to Kleinian Kerr-Taub-NUT. So in 2-2 signature, we have this diffeomorphism that can add or remove your angular momentum parameter. And it's a fully real diffeomorphism. There's kind of Lorentzian tricks like the Newman-Jans shift and things that involve a sort of algorithmic procedure. This is a fully real diffeomorphism. It's sort of distinct from Newman-Jans. And really interestingly, we were able to find some rectangular coordinates in that they reduce to flat space rectangular coordinates in the and then goes to zero limit. Where this diffeomorphism just takes the form of a shift in the z coordinate binding. So there's a really nice set of coordinates where we can add or remove angular momentum from our Kerr-Taub-NUT solution with just a shift of z binding. Okay, great. So for a summary of that, our 2-2 signature Taub-NUT and Kerr-Taub-NUT spacetimes are self-dual when n equals n. These self-dual cases were interesting. Number one, because this were Penrose diagram for self-dual Taub-NUT was kind of like what we would have guessed a 2-2 black hole looks like. The Penrose diagram for black Klein space is kind of half of black Minkowski space, and somehow our self-dual short shield is half of a usual short shield black hole Penrose diagram. And also there exists a real diffeomorphism that maps between Taub-NUT and Kerr-Taub-NUT. And there's a really nice coordinate system where we can realize that shift just by adding a to our z coordinate. Any questions? Yes. So the one distinction is we don't have this diffeomorphism in the non-self-dual case. We have it in self-dual and anti-self-dual, and I guess if you decompose your metric into a self-dual plus an anti-self-dual piece, you could individually act on that, but then that's not really acting on the metric. If you have to act on the self-dual and anti-self-dual parts separately. So yeah, so that was one reason why it was interesting. We found the Penrose diagram for a few other cases. They weren't as kind of fun and black hole to me as this one. But you know, that's a sometimes drawing Penrose diagrams is more part than science, I suppose. Next coordinates. So I'd say that's the two. No idea. Yeah. Yes. The only one we found with the sort of expected black hole features of a horizon and singularity. Yeah.
You said you had Toruses for one of the diagrams. Is that a consequence of the duality again or you still get Toruses for?
No, you'd still have Toruses. That's a consequence of essentially if you take your 2-2 spacetime, if you're able to write it in a way that you have one of your timeline coordinates is not compact, one of them is compact, and similarly for the spaceflight, then at every point in your spacetime you can say, okay, I have some surface that's the compact direction in time and space.
That sounds interesting because I had some reasons to expect that Toruses only happen in the horizontal.
Okay.
That's not the case.
Sure. Maybe we can talk about it. It's not a square torus at every point. Just if
You said that like here, like the angular momentum appears from large diffeomorphism. So I don't know. Would you expect that it would be something like the 40 case where the gravitational the part of the metric that dictates the gravitational memory effect also it's related to a large diffeomorphism, but it's also something that you can physically measure, or it's actually pure gauging.
Maybe there's we thought quite a bit about how to. There's some amount of trickiness in relating so this angular momentum parameter I'm talking about is our interpretation of it is the quick rotation of the Lorentzian angular momentum.
Okay.
But there's some kind of it's a little tricky to actually sort of match the boundary in 2-2 to the boundary in 3-1. As we took it, we did some quick rotations and that theta went to infinity and that mixes up. You're not.
Yeah, but in your space time, the diffeomorphism that you do is a large diffeomorphism.
Yes.
So potentially maybe you can measure differences in that parameter.
Yeah. I think that's valid. I guess I'm trying to think of in the space-time, the angular momentum in our 2-2 space-time, the angular momentum parameter is we don't have fully an understanding of it as angular momentum in 2-2 because it's kind of it's not super clear to think about what surface we're integrating them. Yeah, it's if you try to do conserved charges, it ends up 0 or infinity, all of these things. So
okay,
yeah, so I think there's an interesting question there, but
okay.
Okay, great. We'll move on to the next part. Yeah, so pivoting from our global analysis, we'll look at now connections to amplitudes, our other sort of next motivation for working with signature. So a very, very abridged history lesson on connecting classical spacetimes to scattering amplitude. In 1973, there was a paper by Duff where he was able to take off-shell Feynman diagrams and reproduce the short-shell solution. Ideally, we'd like to look at on-shell conditions. So there was recently renewed effort to look at how we could reproduce classical black hole spacetimes from on-shell scattering amplitudes. And a very abridged list of authors here. There's more references in the paper. But in the past, what folks have done is kind of indirectly matching your black hole spacetime to some amplitude. And the kind of processes you do, you would look at, say, a Lorentzian signature where the sort of best you can do is a 4-point amplitude. You could take a black hole or a massive particle representing a black hole, scatter it with some test particle, and then look at observables from the scattering amplitude, like the scattering angle of the test particle. And then separately, you could look at a test particle scattering in some black hole background and then match those observables. So there are correspondences that have been found, but for the most part, they're indirect in ways like this. So to pivot, what we wanted to do is show that the order G engine constant, order 1 engine constant, part of a stationary metric like Schwarzschild or Kerr-Taub-NUT or just Kerr, that can be obtained directly from a corresponding on-shell scattering amplitude. So they kind of talk about this in this kind of stationary limit where our massive particle has approximately the same incoming and outgoing momentum, and then some emitted graviton. These are the sort of 3-point amplitudes we'll be thinking about. Other things we did, we explicitly checked that this procedure reproduces the linearist metric for Kerr-Taub-NUT. And also there's aspects of this project that tie back to the global part where this amplitude story really motivated our choice of analytic continuation, as well as why this diffeomorphism from the previous partition makes sense. So to go through the setup, I'll start in Lorentzian signature and then we'll figure out how we want to rotate. So starting with my metric, we're going to focus on this H nu, the order G part of the metric. And I'll start in some rectangle angular coordinates that are induced by flat space. Since we're just looking at the order G part, we can change H by linearized diffeomorphisms, as long as we're careful when we want to compare things at the end. So this is nice because we can move to harmonic H, given by this condition, where Einstein's equations at the linearized order become very, very simple. So we want to extract, where this is some conserved source that's given from the Einstein equation. So we want to solve for, we want to solve for H. So using some propagator to extract H from the left-hand side of this equation. We end up with this, where now we've moved to momentum space. We're looking at this T is some current. So example for what it would be for Schwarzschild. Now we'd like to, we've got some expression for H in terms of this current. We'd like to be able to connect that to the scattering amplitude. So there's already this nice correspondence in Lorentzian signature between the classical limit of an endpoint graviton emission amplitude, so some amplitude with a number of massive particles and at least one outgoing graviton. We can write it as the graviton polarization times some on-shell current. And this was done in these papers. It can also want some motivation just staring at the equation. If you think about taking soft limits for the graviton on each side, the left-hand side kind of is soft theorem, taking soft limit of amplitude, and the right-hand side memory effect. Taking that limit for current. Now here I've written for n greater than 3. This is, of course, a Lorentzian expression. When n equals 3, we'll see for our stationary spacetime with this condition on the current, as Ricardo mentioned in his talk. If we want to talk about a stationary spacetime with this correspondence, we'll run into problems in Lorentzian signature because, number one, as I mentioned, we can't have a nice 3-point amplitude for real momenta in Lorentzian signature. And that failure is kind of realized on the right-hand side in that we can't have an on-shell current that also has K naught equals 0 in Lorentzian signature. These conditions can't simultaneously satisfy. And the way we sort of dig ourselves out of this hole is that moving in time space via analytic continuation of this expression here, both sides can be non-zero. We can solve our kinematic constraints, and for a 2-2 signature metric, we can have this condition for a non-zero graviton momentum. Okay. So just to sketch out how we actually go about using this, we'll start with our Lorentzian expression, insert our condition for what it means to be stationary. We'll do a Wick rotation that corresponds to our earlier Wick rotation if we move from our global coordinates to these x, y, and t coordinates. And here's another paper that did a different continuation but similar results. Now we have some expression. We can take our expression for H in terms of the T current. And I'll skip some steps. We can integrate out the remaining complex guy using contour integration. We can reparameterize our remaining momenta. We'll find this expression, which I can translate for you schematically. We can write, basically by reparameterizing this, we are writing our integral in terms of a k for which k squared equals 0. So we're able to find that our metric H is given by the integral over on-shell stationary momenta, stationary being at k naught is 0, of our currents where our current is evaluated on null momentum. And since our current's evaluated on-shell momenta, we're going to be able to use this point we had earlier, where we can connect it to a 3-point amplitude. Perfect, yeah. So since it's evaluated on-shell, we can take this correspondence with a classical 3-point amplitude, where the form of this amplitude has been studied. I'm suppressing some gauge choices for our polarization vector and numerical factors, but I can talk about those later. When we have a 3-point amplitude, the n sort of corresponds to the massive particle, A corresponds to its spinning, and this nut charge comes in a parity-dependent coupling. So because of this, and the kind of connection between self-duality and like the velocity of your graviton, it turns out that this plus will correspond to a self-pole source, and the minus will correspond to an anti-self. Great, so putting everything together on the side, but we can write H as the sum of a self-dual and an anti-self-dual part, each of which can be written, I've just put it schematically here, as some integral over on-shell stationary momenta times our 3-point amplitude, which is something of this form on the right, that looks schematically like this. So that's how n and A. And these momenta, these 3-point amplitudes are obtained via a classical limit of sort of graviton emission amplitude. Yeah, and just to summarize, the stationary metric, perturbation H is free everywhere. That's what it means for TB on shell or everywhere. We found this, as I mentioned on the previous slide, for how we express our metric in terms of 3-point amplitudes. And finally, I'll note here that the diffeomorphism between Taub-NUT and Kerr-Taub-NUT emerges very naturally. It makes a lot of sense from this amplitudes picture why we would expect this. And this is because if we wanted to add angular momentum, it comes in this exponential factor in the momentum, in the 3-point amplitude, sorry. Which just putting it into this interval very naturally adds to our x coordinate there. So we have x mu here, that's t, x, y, z, and we have the a mu vector that say it's just a spin a in the direction. It very much just adds to your z coordinate. I'll move on to very quickly, so we're in progress and for questions. Yeah, so now we wanted to ask, is there a way to translate this bulk construction to something on the celestial torus? This is work in progress with Alfredo, Mina, and Andy. So we can recast our previous result in maybe a slightly nicer form, something that we're a little more used to seeing, where we have our integral over our graviton momenta parameterized in terms of the usual null momentum parameterization on the celestial torus coordinates W. And we can absorb this little stationary condition into our Euclid function. We can translate this rewriting into a formal primary basis where we have the analytic continuation of our usual formal primary wave function. And then the idea is that, okay, if we're equipped with this new rewriting of H on, in some sense on the torus, in terms of a mode expansion on the torus, coordinates W, W bar, we're looking to find some quantum state on the torus that will give us in an expectation value a reproduction of the classical metric. Yeah, so this sort of, you expect we want to construct a classical thing from quantum state, billable coherent state. Yeah, and in interest of getting everyone to lunch, I'll end there, but we're happy to talk more. Yeah.
probably a very naive question. So in Lorentzian signature, any pre-rated field can be reconstructed characteristic data.
Yes,
It's dry.
yes.
These integral formula you're writing down in 2-2 signature, are these just like 2-2 version of the Kerr-Taub-NUT model?
Essentially, yes.
So
But-
A is like characteristic.
Yes, yes. And the distinction in Tutu is that in Lorentzian signature, you have sort of your H is free or rated when you're asymptotically far away. Whereas in Tutu, it's actually free everywhere. And it satisfies delta or H equals zero.
I guess maybe this is what you're saying, but I guess I would have said something like Schwarzschild and Lorentzian is not rated.
Yes.
2-2 is.
Yes, exactly.
Any other questions? Okay, thank you very much, Erin.
Thank you.
Okay.
Sorry, I missed.